Well, welcome back, everyone. In the last lecture, I was talking about how you might display the results of data when you have effect modification. I said the best thing to do is to give the reader separate answers for separate groups of people. Present straight and specific, sex-specific, age-specific results if you think sex or age is an effect modifier. I said what you probably don't want to do is pool those different numbers into one single average using Mantel-Hansel's formula. But I said there is another option, to get one number to describe the average effect of that risk factor, that exposure, that treatment in a specific population. That's what standardization deals with, and that's what I'd like to talk about now. And again, this is a review because Marcello's already talked about standardization. So what are the steps involved in standardization? And going back to what Marcello's been talking about, I'm talking about direct standardization. So what do? I start out by selecting a population called a standard. And I'm going to describe the effect of an exposure in that particular standard population. Now, how do I do that? How do I take into account effect modification? I stratify my data by that factor. And say I'm thinking of age as an effect modifier. I stratify my data into age groups. Within each age group, I don't measure risk ratios as I did when I did Mantel-Hansel calculations that get averaged together. What I'm going to measure in each of my strata are risks or rates of developing disease. I'm going to, within these separate age groups, I'm going to look at the risk or the rate of developing disease among the exposed people and among the non-exposed people. So for each of my subgroups, each of my strata, I have the risk or rate of developing the outcome if you're exposed or non-exposed. I'm going to use those risks with the standard population to estimate a couple of things. I'm going to estimate what would happen in the entire population if everyone was exposed, say if everyone was a smoker. I'm then going to estimate what would happen in that same standard population if everyone was not exposed. And so I'm going to come up with two numbers, the expected number of events in that one single population if everyone was given the exposure, and the expected number of events in that one population if no one was given the exposure. I'm going to compare those two numbers to describe what's the effect of the exposure in that standard population. Everything is linked to the standard, and that's why it's a useful thing to do when you might have effect modification or if you have confounding. It's a way to adjust for confounding, but in this case, it's a way to display the effect of a risk factor when you have effect modification by describing its average effect in a single specified population. Well, before I leave this slide, what I just said with standardization is giving me an estimate of how many events, outcomes would happen in that standard population if everyone was given the exposure. It's also going to estimate how many events, how many outcomes would happen in that same standard population if no one was given the exposure. Well, gee, that sounds like what we call counterfactuals when we talked about confounding. And exactly that's what standardization is going to basically do. It's going to be able to estimate counterfactual outcomes and counterfactual risks for a single population if everyone is given the exposed, and for that same single population if no one is given the exposure. Okay, so what are the choices for this single population? Well, typically what's done is we use an internal standard. We might use the full data set, everyone in our data, both the exposed and non-exposed people together, or we might just use a portion of our data set, just the exposed people or just the non-exposed people as our standard population. No matter which one we pick, standardization will give us two values, the expected number of events in that chosen standard if everyone was given the exposure, and then again if no one was given the exposure. You could use an external population. I think that's what Marcello might have been referring to when he talks about vital statistics. Our country every year publishes mortality rates that are standardized year to year. And so what they're using there is a population, a standard population that existed in the country in a certain year, and standardizing all the mortality rates from different years so that one single standard population. No matter which population you choose as your standard, when you do standardization, what you're getting is a description of the average effect of the exposure for that chosen population. That means if you change the population and do another calculation, another standardization with a different population, your results might change. Your comparison to the expected events if everyone was exposed versus no one, when no one was exposed for one population, might give you a different answer if you used a different population. Well, I'll show you, I'll take you through some steps of standardization in a minute. And Elizabeth is going to take you through the process of standardization also in your one of her stated demonstrations. But before I leave this, there's one last thing I want to talk about standardization, linking it again to this idea of counterfactuals and this notion of causal inference. If you have no other confounding factor, you're standardizing, say, by age. If no other factor like sex or blood pressure are confounders in your data set, then when you standardize, what you're really getting, as I say, are estimates of counterfactual outcomes. What would happen in the standard population if everyone had the exposure, and then again when no one had the exposure? So standardization is linked to this notion of counterfactuals, linked to this notion of causal inference. Mathematically, I'll also show you in a coming lecture that standardization is linked to this idea of inverse probability weighting. Basically what standardization does, as you'll see this in an example in a couple of lectures from now, is it reweights your data set. Reweights the exposed people so they represent the entire standard population, reweights then the non-exposed people to represent the entire population. So if you're standardizing by age, each of your age groups, your exposed individuals are then reweighted to represent everybody who's in that age group in the standard population, and likewise the non-exposed people in that age group are reweighted. So weighting is related to this notion of standardization, and you'll see it's related to another topic that I'm going to be talking about next week. So I'll bring this up in an example in 2 lectures now as a bridge for what we'll be talking about next week. But let me now go through an example of standardization, and I want to do it with you. So in the next slide, I'm going to present some data, and I'm going to ask you to do some calculations to do a standardized analysis, and then I'll show you the results. And then finally, you'll see in a Stata demonstration, all this can be done for you with Stata. But I'd like to take you through a hand calculation first. So I'll see you then.